Hello everyone, my name is Camille and today I'll be talking to you about the link between visual motor learning and proprioceptive impairments after stroke. Stroke can often leave individuals with impairments in moving and sensing their arm that affect their ability to perform activities of daily living, such as eating with a fork. Many individuals with stroke seek rehabilitation to regain sensory and motor function, where therapists often use visual and proprioceptive cues. Proprioception being the sense of body position and motion without visual input. Learning is a pillar of rehabilitation, and visual motor learning involves both visual and proprioceptive feedback. However, the ability to use visual and proprioceptive feedback to learn and improve arm movements can be impaired after stroke. Proprioception may also impact the ability to detect errors and learn from them. Currently, we don't have a way of knowing what types of therapy work for different individuals, so everyone gets similar therapy. To understand why this works for some but not for others, we need to look into what makes individuals different. Precision medicine strategies like this have not been applied in rehabilitation, as many studies look at group averages, which don't tell us anything about individual learning abilities. Given that visual motor learning involves both visual and proprioceptive feedback, this raises the question of how proprioceptive impairments interact with the ability to learn and improve movements. To answer this question, we conducted an observational study where we examined the relationship between visual motor learning and proprioceptive ability amongst participants with stroke and healthy controls. We predicted that impairment types would emerge in which participants may have impairments in visual motor learning, proprioception, both, or no impairment. We had 31 healthy controls and 6 participants with stroke perform 2 tasks in a Kinarm exoskeleton robot. Participants were seated in the robot and could then interact with targets on a screen via a cursor that was aligned to their fingertip. The first task was a visual rotation task. Participants began by performing baseline or normal reaching movements as they reached to one of 3 end targets. We then applied a 30-degree counterclockwise rotation to the cursor, where full adaptation required participants to reach 30 degrees clockwise to reach the targets. Because the cursor was dissociated from straight movements, this required participants to learn to modify their movements based on the error they experienced. This allowed us to quantify the amount of learning from errors, which we did by measuring the initial reaching direction in each reach. The second task was the position matching task, which measured proprioception. In this task, the robot guided the dominant hand for controls, or stroke-affected hand for participants with stroke, to one of 9 positions. Participants then had to mirror match this position with their other arm. After completing the task, measures such as the distances in the X and Y direction were used to calculate an overall standardized task score. So here we have some hand paths demonstrating reaching movements made by a control and a participant with stroke. Note that we split up the movements to each target to be more easily visualized, but participants always started from the same start target in reality. So we have baseline reaching movements here in black and late learning in red and blue, and the dotted lines here indicate the 30-degree rotation. So as you can see, by late learning, the control learned the rotation to a much greater extent because they're making much straighter reaching movements. Now let's compare this to proprioception. So here we can see that this control performed well on both visual motor learning and proprioception, and this participant with stroke appears to be impaired in both. But is this always the case? Our initial findings point towards the idea that impairments in proprioception may not preclude normal learning and vice versa. So here we have position matching task score plotted against initial angular deviation, and normative ranges containing 95% of the control data were calculated for both measures. Participants with stroke scoring outside of the normative range were considered impaired on that task, represented by the darker regions here. Participants with stroke demonstrated impairments in proprioception, both visual motor learning and proprioception, or no impairment. So here we can see that these different impairment profiles are beginning to emerge within these 6 participants with stroke. And this finding that visual motor learning performance may not depend on proprioceptive ability indicates that there's a learning impairment present here that may not rely on proprioception. It's important to note that this is a small sample of stroke participants. However, our findings highlight the importance of assessing motor learning, as impairments may not always be captured by measuring proprioception in the arm. Now that we have profiled these types of impairments, we may be able to better understand individual impairments in proprioception and motor learning after stroke. And as we continue to collect more data, the assessment of motor learning impairments may, in the long run, help inform how therapy is planned and delivered to individuals recovering from stroke. And here are some references for those who are interested. And finally, I would like to give a big thank you to my supervisors and fellow lab mates who helped me with this research.